Okay. Thank you. Okay, so well, do you need to have a time for them during the break? If you have any questions about your exam, maybe you'll come back again in the middle. Finished. Okay, so you can come back if you have any question about your quiz too. You can seek teaching assistant around 5:20. All right. Okay. Thank you. Right. So um the average is 71, right? The average is 71. So quite all right. And I guess it's our final times, final hour, final 2 hours, final courses. So yeah, let's continue our lecture and let's finish today. But because I want to finish it today, I still have about 20 pages. So I need to be quick. So last time we talked about how to draw a Mohr circle, right? And this is the question. And the question was the compression 50 megapascal and tensile in y direction 10 megapascal and 40 megapascal for shear. And then we can calculate sigma average and R, and we can set up the Mohr circle, right? So that's it. And then it asked us to get the we need to figure out where is the A point, right? A point. Point A for the plane A. Where is the plane A? The plane A has 50 megapascal compression and 40 megapascal for shear. But the shear in this, if we focus on plane A, this is a negative shear. So negative 40, and negative 50. So you can see here it's 30, in total 50. Okay, compression, of course, it's minus sign. And then this is minus 40. So above the y axis, above the x axis. So we can have this point A, okay, and which is theta equal to 0 degree. All right, so we set this point for plane A. Okay, then we want to get the AO P2. Where's the P2? You know that, all right? The P2 is the most left point. This is P2, right? Principal stress 2. And this is P1, of course. Okay, the right-hand side. So I want to get this angle. It's called the angle AOP2. Okay, I want to get the angle AOP2. And what is angle AOP2? We can using the tangent AOP2 equal to what? Equal to 40 divided by 30, right? Because we can have a here. This is we have the height here, right? 40, and down below 30. So you can get this angle. Angle is 53.13 degree. Okay, by typing this into calculator, AOP2 equal to 53.13 degree. Okay, so we can get where is the now we are kind of ready to get the first question. Theta 45 theta, excuse me, theta 45 degree, which is point D, right? Point D. In the real world, if we go up to 45 degree, which means that in the circle, you get 90 degree in the same direction. So we are going to get the angle with 90 degree, right? And what is a 90 degree? So I will say this point is D, and this angle is 90 minus 53.13. So it's 36.87. All right. So we can further get that angle DOP2 equal to 90 minus 53.13 degree. You can get 30. So that's how we get this angle. Okay. And of course, I will say this angle I will using pink. Okay, pink highlight later. Okay, or I can write it, draw it right now. This is the 45 degree. 45 degree. 45 degree. X1, and this is X. Okay, so 45 degree, and I will say this plan is plan D. This is plan D. Okay, the plan D, we above, counterclockwise rotated 45 degree. And in a circle, we counterclockwise 90 degree. Okay, so what is the value of it? Again, we can use the triangles here. Of course, vertical triangle. So let's get sigma x1. Sigma x1 actually is the coordinate of the point D. Okay, minus 20 minus 50 cosine 36.87 degree equal to minus 60 MPa. Okay, so you can see that minus 20, right? And 50 times cosine 36.87. So you can get this height, and this height is this point, this point, this point, the total length of this x coordinates, and tau x1 y1 equal to easy, right? R sine 36.87 degree, 30 MPa. Okay, so now you are ready to draw this. Oh, sorry, it's minus. Minus become compression, right? So it's 60 MPa compression. Of course, the opposite side will has exactly the same value, and in the D plan, you have tau x1 y1 30 MPa. 30 MPa is positive, right? So your positive value will be here. It's 30 MPa. Of course, you will have all the shear come in pair, right? All the shear come in pair, and they all are the same value, 30 MPa. And where is the y1 axis? We didn't know, we haven't know yet, right? Know yet. So we can say this is the point. We say E. Okay, we say E. This is point plan E related to D point, which is 90 degrees in the real world. How about in a circle world? It will be double it, right? So it's become 180. 180 degree opposite side. Okay, opposite side. And then you can use the same angle in the opposite side. E point. This is theta equal to 135 degree. Okay. Right. So theta equal to 135. Theta equal to 135 degree. Again, it's easy, right? You use the light blue triangle. Sigma x1 equal to, now it's still x1 because we use E as a focus, main plan. Okay, this is our focus. We're still using sigma x1 rather than y1. Okay, so again, where is the coordinate of this point E? Sigma x1 minus 20 plus 50 cosine 36.87 degree, 20 megapascal. Okay, good. It is positive. Okay, positive. You can see here it's positive 20, right? Positive 20. And you see here is negative tau x1 y1. You see this is going to the kind of right hand side, right? So it's kind of going down. If you using your head, bend your neck to see that it's going down. So it should be negative. Yes, right. So everything's matched what we expected. So here will be 20 megapascal. Again, please don't write down the sign when you draw the direction, right? So you don't need to draw, if you draw the direction of the force or stress, you don't need to adding up the sign or positive sign. No, you just keep the value because minus sign and positive sign indicating the direction. Okay, so now you finish the problem 1. We have problem 2 and 3. 2 and 3 basically, again, very, very easy, right? Principal stress, P1 and P2. All we need to do just get the coordinate. You know how much is it, right? 30, right? This is, what is that? 70 minus. Okay, so this, you can do it almost immediately. So now in the next page, I will copy this small circle to the next page. I need to copy this page, this small circle to the next page, and then we'll continually use this in the next page. All right. 好，这边应该我觉得都还算听得懂吧，哈，都蛮简单的。那总之，你会了这个 concept 以后，你只要画出这个圆，你什么都可以算出来了，而且全部都是 几何的算法，而不是你的背公式的算法。好，非常非常的我就觉得蛮好懂的啦哈。那接下来就直接看主应力跟最大剪应力。OK，next，right. So I just copy here and then adding more. Principal stress. Okay, theta P2. Okay, we have done that, right? 53.13. But this is the angle in the circle wall, right? So don't forget divide by 2. Okay, so you need to be careful. Please don't just write down 53.13. No, we need to, because this is circle world, right? Circle space. So now P2 is 26.6. So now I draw this. This is 26.6. And okay, this is the element. Okay, and what's that? Minus 70, right? Minus 70. I can determine this by our eyes, right? 20 and 50. R is 50. Sorry, 70. 70 MPa. 70 MPa. Okay, and where's P1? Of course, it's in 90 degree, right? 90 degree, where is that? In the right hand side, 30 positive. Easy, isn't it? 30 MPa. Okay, done. Done. Very easy. How about tau mix? Tau tau mix again, very easy. 2 sigma, sorry, 2 theta s. 2 theta s equal to 90 plus or minus 53.13. Right? So, well, so now I can just select one of them. 90 plus 53.13 and 143.13 degree. So theta s equal to 71.6. Okay. Maybe you will ask why you know that you would choose positive rather than negative. Yes, you can do that. 90 minus 53.13. Okay, is 36.87. And you can divide them by 2. So you can get another theta s, no problem. But here for me, it's I prefer that to make it relatively bigger value. It's okay. Don't worry. Anyway, so I just using 71. A little bit higher, right? 71. The 71 x1, and this is 71 degree. 71.6 degree. Okay, so now you have a okay, 71.6 degree, and you will have here and here called tau mix. And tau mix. Okay, so you can see that from here, theta equal to 0, okay? And you rotate 2 theta as 143.13. So it should be around here, 90, and it's 53.13 degree. Okay, so this theta as 71.6 is this point. Okay, so here this point and this point. Okay, yeah, that's how we find this. And then this is positive tau. Okay, positive tau. So it's positive tau. You see in the main focus phase surface, it should be upward. Okay, and the value will be 50 MPa because it's R, right? We can using our eyes. Just by looking at it, we can get the value. So that's how elegant. That's so elegant that Mohr circle can be 50 MPa. Okay, but we haven't done yet because in a shear force, in the maximum shear force case, we still has normal stress contribution, but we don't have any shear stress component in principal stress case. Okay, so we haven't done it yet. So we still need to get the x coordinate for tau max for these 2 points. But it's okay. We can still see that 20, right? Minus 20. So for both of the tau max, both of them have minus sigma x1 for 20 megapascal. Okay, very, very easy. 20, okay, and 20, and 20. Okay, so they are all 20 megapascal, 20 megapascal, 20 megapascal, 20 megapascal. Okay, that's it. That's it. All you need to do, just find out the correct point and corresponding surface in the small circle world and real world. Connect them. Don't forget the theta will be double in the circle world and everything. You're just using your hand calculation. You can get that very neat, very good. All right. So, next sections, I would like to introduce the Hooke's law. Okay, the Hooke's law is quite simple for you, but now because now we need to take the plane stresses into account. So something relatively different. Okay. I hope the Mohr circle will be. Mohr circle is really important, and it definitely appeared in your final exam. And it's easy, and I hope everyone can understand this. Right. Next, Hooke's law for plane stress. Okay, the strength due to the plane stress, you can see that this is the plane stress. Only x and y direction components is here. So if you consider that sigma x to do the tensile, everything for assume positive right now. All right. So sigma x positive. It will contribute the elongation in x direction. Of course, sigma x divided by E. You know that the Hooke's law is E epsilon equal to sigma, right? So if you want to get the epsilon, you just put the E below the sigma. All right, so that's the first contribution. And another contribution for this, or kind of negative contribution, is that sigma y is going to pull to up and down. So the x-axis should be shrinking. Okay, so it's kind of Poisson ratio effect. So you see, sigma y divided by E is the strain along the y direction. But if you times the minus nu minus Poisson ratio, it is the contribution to reduce the length in x. Okay, so you see, sigma x has positive contribution, but sigma y has negative Poisson ratio contribution. The same story in this epsilon y. And then I would like you to focus on this. Although there's no stress along z component, but it doesn't necessarily means that there's no epsilon z. You see, even you don't have anything along z direction, you still has the epsilon z because of the Poisson ratio. Okay, because you pull sigma x, it will reduce the z direction length. If you pull this y direction, you will reduce the z direction as well. So you have both negative contribution due to the Poisson ratio in x and y directions. So you need to be careful. Even plane stress has z strain. Okay, this is really, you need to be very, very careful. 中文讲一次，就是因为 z 方虽然 z 方向没有 stress， 但是 z 方向却有 x 跟 y 的应力所造成的普松比效应。因为你 x 方向一拉 ，z 方向一定会往内缩嘛，所以即使没有 z 的应力，你有 x 跟 y 的应力，它也会造成 z 方向的应变。那是普松比的应变，所以千万要小心哦。Okay, be really careful. And also shear strain. Wow, this is easy. Okay, just changing the angle. Gamma xy is the angle. So tau xy divided by g is the gamma xy. So you can imagine that this is the cubic. Okay, this is a cubic, typical cubic for stress element. Before the stress, before the loading, you have A, C, B as a original length, okay, for 3 edges. After that, after the loading, you will have A epsilon x for the elongation, no matter what, okay, and B epsilon y, no matter what, C epsilon z, no matter how this is negative or positive, both okay. So the dashed line is the cubic after the loading. Okay, so now we are going to see what this strain give us. Okay, so some example later. I will give you the Hooke's law for plane stress. Some special case. Remember that if you have epsilon. If you're just considering tau xy equal to 0, okay, you only have sigma x and sigma y non-zero. So you will have epsilon xy, epsilon x, epsilon y, epsilon z. These three combine together. Okay, combine together. So if you just combine them together, you want to determine sigma x. Okay, so you can use kind of manipulating these two equations. You can obtain sigma x equal to blah 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 blah. OK， 就把它相乘减起来就好了啊。乘上一个 nu， 然后例如说你要把 sigma y 消掉，你就这边乘上一个 nu， 它就会把这个 sigma y 消掉。 然后后面就会多出来，然后你就可以得到这个式子。Okay, so using these two equations, we can obtain sigma x and sigma y independently. Okay, and you can see that sigma x related to epsilon x, epsilon y, and material properties. Right, and well, next page will be your special example. Yeah. Oh, sorry. That's it. So now let's see volume change. Because you see, after your loading, your volume will change, right? So your original volume, V0, equal to ABC, easy, right? But volume after the deformation will be A plus A epsilon x times B plus B times epsilon y plus times C plus C epsilon z. So when they times together as the new volume is volume after the loading, volume after the deformation, we call V1. Okay, maybe step one or after loading one, you can have ABC times 1 plus epsilon, 1 plus 1 epsilon y, 1 plus epsilon z. And then if you expand them, you can get this long and ugly equation. But don't worry, because we assume that strengths are small. So you can see that two small things times together, we can neglect them. And even neglect them. This one, neglect them. Okay, very easy. So we can say V1 is approximately ABC times 1 plus epsilon x plus epsilon y plus epsilon z. Okay, that's it. Then you can see that the change in the volume of the element, the difference of the element, V0, V1 minus V0 equal to this ABC times epsilon x, epsilon y plus epsilon z. And then the change per unit volume is actually, we use this divided by V0. So you see, what will it be? It is epsilon x plus epsilon y plus epsilon z. Oh, you see, this is very interesting. Okay, you see, epsilon x, epsilon y, epsilon z, sum them up together. It will be the change per unit volume, or you can say volume increase ratio. 体积增长的百分比，体积增长的百分比竟然就是 x 跟 y 跟 z 的 strength 相加就好。你看哦，人家是体积的增加率哦，竟然跟你的应变的3个方向的相加起来一样。哎呦，应该说靠近接近，还蛮有趣的吧？ And remember what I said, the strength and stress can be written down as the matrix. Okay, remember that if you remember this, epsilon can be written down as a matrix form. Epsilon 1 1, epsilon 1 2, epsilon 1 3, and epsilon 2 2, epsilon 3 3. 2 3, and epsilon 3 3. Okay. And then this is a symmetry. Typically, It is symmetry. Okay. So this is a general strand matrix looks like. And then the diagonal term, sum them up together. If this diagonal term sum them up as zero, which means that no volume change. Oh, interesting. 好，这边要中文讲一下，就是还记得我之前有说过 strain 跟 stress 应力跟应变，它可以写成矩阵的形式吗？好，因为它那个 x y 其实可以把它写成1啊1、2这种东西，其实你就把它写成矩阵就好。那这矩阵通常会写成这样子，然后它通常是对称的啦哈，通常啦哈，因为你在做一个就是紧切啊，或者是做一个拉伸的时候，你一定是同时两边都拉嘛，同时两边都切嘛，然后所以这边的简历的项1、2跟1、3跟1、2、3它是对称的。好，那这时候我们就写出这个矩阵。如果今天有一个东西受到应力，然后它就有一个变形，我们可以用应变的矩阵来表示它的变形。那这个变形，它可以直接告诉我们说，你只要看它这个东西有没有体积有没有增长，就看它的对角线相加就好。如果它加起来0，表示说它完全没有变化的体积。什么叫加起来等于0？有的是正的，有的是负的，有的是正的，哎，加起来然后正好抵消了，就表示说它这样子的运动状态下这体积是不会改变的。但是如果今天是加起来2，哇，表示说它体积增长2倍，它太夸张了，它不可能。通常都加起来都是大概1.0多啊，什么之类的，然后1.01啊，大概是这样。比如说它的体积增加了0.001倍啊，大概是这个样子。OK， next， why we are bothering to discuss the epsilon 1 or epsilon 2? Why? Because if you have the epsilon, which means that you have displacement. If you have displacement, which means that your load times the displacement has the energy stored in your material, right? So we are going to talk about strain energy density due to the normal stress, in-plane stress. Okay, strain energy density is the strain energy per unit volume. I guess we learned that before, right? You remember your strain energy density is small u, and this is the area of the sigma and epsilon diagram, stress strain diagram, right? So you can imagine that you have the sigma y, you have the sigma x, okay? And you do the volume change for this, okay? So again, work done by stress on x surface, okay? X surface, your x surface, how to determine the work. Force times displacement, right? So what is the force? Sigma x times the area. So sigma x times the BC. So this is the force. Force. Sigma times area. What is the displacement? Length change, right? A times epsilon x. A times epsilon x. So they are the displacement. Displacement. Okay? And of course, force times displacement divided by 12, which means that it's an angle, right? I mean, triangle, the triangle area. All right? And then you need to divide by the total the total unit volume, right? The volume. So you divide by ABC. But be careful. You still need to add in the work done by the stress on the y surface. Exactly the same thing. Sigma y times the surface AC and B epsilon y. So you have two work, sum them not together. Okay, you have total strain energy due to the normal stress. So you see A times B times C, A times B times C. Okay, right, so you can see both of them, sum them not together, you can get this. And then this is a total strain energy, not strain energy density. So you need to divide by ABC. Ta-da! So your U will be half sigma x epsilon x, sigma y epsilon y. That's it. Okay? Not too difficult, right? Not too difficult. All the proof in the mechanics of material, they all follow similar, flow. Similar flow. Stress times force, force times displacement become energy. Okay, that's it. Now, after we discuss the plane stress, strain energy density due to the normal stress, don't forget, we still have shear stress. Shear stress also gives us strain energy density. Okay, so next page, I'm going to add in this to shear stress energy. Okay, so this is normal stress strain energy here, and we can use in shear stress here, U2. Of course, again, half tau gamma U. Okay, so tau xy, gamma xy divided by 2, your triangle area, okay, in the shear stress, shear strain diagram. So then, so since normal strain and shear strain are independent, the strain energy corresponding to the two strains can be added. Okay, maybe you will ask, don't you remember I said that your energy due to the loading cannot be added, right? But now you add it. Why you just added U1 and U2 together? Sorry, U1 U2 together become your U. Why this can happen? Because they are independent. Okay, so normal stress make the volume change, but shear strain never make the rarely make the volume change, because you only twisted the angle, you didn't change the volume. So actually normal stress and shear stress are independent. OK， 这边要讲一下，还记得我们之前在第2章讲的时候，我们说shear strain 讲错了 strain energy 应变能不能这样乱相加，什么拉了一点点再拉下一点点，你不能把它，你拉1单位拉2单位不等于拉3单位哦。还记得我那时候讲这件事情。但为什么这边可以？好，这边原因是因为这样，之前是1单位、2单位，然后不等于3单位，那是因为你在同一个状态下，它们俩之间是互相不独立的。但是这边的剪切应力跟正向应力都是独立的，因为你可以发现正向应力它会改变大小，但是剪切应力不会，它只是改变角度而已，它连大小都不会改。好，所以这2件事情其实是几乎是没有关系的啊，没有关系的。所以说这边就是可以相加。好，那如果你觉得有点怪，那可以想一想。Okay, so now I'm saying that U1 and U2, due to the normal stress and shear stress, they are independent, so they can be added together. Okay, so they added. All right. Then, if I want to replace it by I don't want to use epsilon x, epsilon y, and gamma x1. How can we do? All we need to do, using what we learned in the previous page, epsilon x equal to this. Yeah. We learned this before, right? In the previous few page. Okay, so if we can know this, we can substitute this, and then we can get the final form that no epsilon required. All we need to do is add sigma x and sigma y and tau xy. Of course, we need some material property, E and G and nu. Okay? So yeah, I can say this is material properties. Green line is material properties, green highlight. And blue, sigma x, sigma y, and tau xy is the problem. Okay, the problem will give you the current state of the shear or the stress element. So now we finished plane stress. We are going to another topic called plane strain. Plane strain is very similar to plane stress and just a little tiny different. Okay. When I was your age, I cannot identify plane stress and plane strain. Okay. I hope I will try to put my best to let you know the differences. Okay. That's 8页. Okay, I don't know if I can finish 13 page in 15 minutes. Anyway, I hope I can. So I guess you see my speed a little bit increased. 有看到我稍微有点加速哈。对，因为我发现如果今天上不完，明天就要上个20分钟，让你们来，会让你们觉得有点对不起你们这样所以我还会稍微快一点点那反正我今天晚上就会把这个上传。那如果你觉得我太快，你就把它调慢一点，或者是如果你觉得太快，你就看 OCW 也可以。不过我讲的东西基本上都跟之前的就是我该涵盖到，应该都有涵盖到。然后如果你有问题的话，你等下也可以问我。Okay, so let's continue. Plane stress. Plane strain. Plane strain. Plane strain called 平面应变. So very similar to the definition we mentioned before. The strain only in the XY plane, 2D. No strain in the Z-axis. So what is a plane strain? The stress element deformation occur only in the XY plane, epsilon x, epsilon y, gamma xy. In the previous plane stress case, sigma x, sigma y, tau x1, y1, right? The only difference, now you focus on strain. No Z component strain. All right. So you can imagine that no epsilon Z. So what does that mean? Which means that epsilon Z can be very small that we can ignore. So the most common case is that a really, really long material. Okay, so the original length of Z is really, really long. So any displacement in Z is tiny compared to its original shape. So no epsilon Z. 你可以想象一个超长的 material 在 Z 方向，那所以 Z 方向的一点点变化的 displacement 的变化，位移的变化 epsilon z 就超小，因为它要除以它的原本的长度。Okay, so I will see you after 10 minutes. Okay, if you have any questions, just come here. 明天早晨，避免像上次一样又突然没有能量。OK，好，希望能在1小时内把平面 strain 讲完。 平面应变讲过，这个东西跟那个平面应变应力差不多，但是它是以应变来看。你的意思就是说，哎，通常你一个材料，你不知道那一个点的应力是多少吧？我们不知道啊，但是我们可以量它的应变，就是它的应变多少。所以在这边会比较符合我们实验上的量测。OK， 那变什么意思呢？通常我们在讨论的是一个就是很厚很厚的东西。你看到平面应变是说 epsilon 是没有 z component 在这里，没有 z。那这是什么意思呢？就是应变在 z 方向几乎等于0，或可以忽略。那什么意思？就是应变其实等于就是伸长或缩短率，对不对？那如果今天你的原本的长度超长，那你给它任何的外力，它的 z 方向就一点点的变形，那它的率就 epsilon z 就会变得非常非常非常非常小，所以就是这个意思。所以不好意思，平面应变的应用的例子，通常就是一个很长很长、截面很长很长的材料啊，大概是这样。所以你可以看到水坝啊，水坝就是它就是一个很城墙啊，一个很长很长的东西，你只要考虑它的截面就好，就可以使用平面应变。所以你想想看，我们的薄膜，那就不能用这个啊，我们材料常用薄膜，不能用平面应变哦，不行哦。你要用平面应力 ，OK？ 好，所以这要小心。Right. So what I'm talking about is that the most common example for this is for plane strain is a long material along z direction. So you will have very long original length, which makes any type of deformation displacement close to zero. I mean, very tiny compared to its original length. Okay, so you can mention that is the material can be a dam or a wall. Okay, how about thin film? Thin film is not this type of material. Okay, it should be plane stress because it's tiny. All right, thin. Okay, this is thick, very thick. Right. So again, in this case, these three values will be known. Okay, just like sigma x, sigma y, tau xy in the previous section. Okay, so and also in experiment, these three values can be measured. Okay, by strain gauge. Okay, I guess you heard of that. So yeah, it will be easy because you can measure the angle. You can also measure the length increment. Okay, so plane strains kind of more close to stress to our real world. Okay, now plane strain and plane stress. What's the difference? So plane stress is that stress has z value. Okay, but plane strain is strain has no z component. It are all zero. Okay, but importantly, you see, in the plane stress, you can still have epsilon z because of the Poisson ratio I told you, right? Or you will have sigma z in plane strain. Of course, again, Poisson ratio, right? Because if you don't have any epsilon z, well, it will be kind of impossible, right? Because you will have it definitely has your own Poisson ratio effect, but you don't have any epsilon z means something kind of constrain it, so it has sigma z. 好，这边我讲一下，你会发现 plane stress 跟 plane strain 非常像，只是一个是 stress 的话，就是 z 的 component 的 sigma 都是为0的 那 plane strain 的话，就是只要 epsilon 里面有 z 的话都为零，这几乎是相反。但是呢 plane stress 平面应力的地方有 z 方向的应变，因为普松比。OK， 这个我也解释过了，在之前解释过了。但是呢，平面应变它也会有 z 方向的应力哟。为什么？如果你今天一个材料在 x、y 方向有任何的应变啊，这也代表它一定有普松比嘛。那可是你的 epsilon z 又为零，表示说你这个材料一定有一个内应力在 z 方向，就把它这样 hold 着，这样它在 z 方向才不会变化啊。所以说你的 sigma z 就是不为零。OK， 如果你要有 epsilon z 等于零这个结果，sigma z 一定会有在那里，就把它 hold 住。OK， 所以就是大家需要注意的地方。All right, so this is the most difficult part in plane strain. All right. We also want to know the orientation. Okay, if you have x and y, if you have the epsilon x, epsilon y, gamma xy as the known value, how can we get epsilon x1, epsilon y1, gamma x1, y1 as the new x1 axis direction component? How can we get that? So this is x and this is y. Okay, and this is x1, the theta. All right, so I want to know if we have epsilon x, epsilon x, epsilon y, and also gamma xy, gamma xy. Okay, you have these three values. Okay, and what will it be in the x1, epsilon x1? What is the epsilon x1? What is that? So we are going to see the red line before and after deformation. After the deformation, how long it increased in x1 direction due to these three contribution. Okay, so that's what we're going to do. 好，我们现在要讲了哈，这三个是我们知道的，在 x 跟 y 跟 xy 方向上的应变。好，但是我想要知道的是，我现在感兴趣的不是 xy， 我是感兴趣的是 x1 方向的应变哦。也就是说，我必须要把这三个人对 x1 方向变形的贡献加总起来，才会是 x1 的方向的应变。OK， 不要忘了这边都是同一个应变状态，所以我们必须要找到就是 x1 原本的长度是这样子，是红色这条线。我现在想要知道就是说，如果今天有 epsilon x， 它会在这个 x1 方向会伸长多少？如果有 epsilon y， 它在 x1 的方向会伸长多少？如果有 gamma xy， 它在 x1 方向会伸长多少？三个加起来就会是 x1 方向的总应变。OK， 这就是我们的 concept。Right, that's exactly what I'm talking about here. So this blue rectangle will be this one. Okay, so now calculation of epsilon x1. Okay, the total elongation along x1 direction. This called ds. Okay, ds. ds is the original length in this diagonal line, this red line. Okay, original length. So this is along x1. So if this is dx, this is dx. Okay, so if the dx elongate epsilon x dx, of course, this is its x direction elongation. What will it contribute in x1 direction? So you can see epsilon x, epsilon y, gamma xy. Okay. So what's that? All these are, this red highline is norm. Okay, we know these three values. We know these three values. So you can see that the delta D is the total elongation along x1 direction. This delta D has three contributions: epsilon x, epsilon y, and gamma xy. Let's see one by one. All right. So you see this rectangle expand in x direction. Is with this dashed line, dashed shape. So let's enlarge a little bit. All right. So let's take a look. Okay. So you see, this is epsilon dx. Epsilon x dx expand to x direction. It make this point expand to this point. Okay, so this is the x1 direction expansion because of epsilon x dx. Okay, so this will be, and of course this this is theta, right? So you will have epsilon dx times cosine theta. So this increment is epsilon x dx cosine theta. All right. So first contribution. If you can accept this, the same story is here. If your rectangle elongates along y direction, and this x direction, this point will move to this point, right? This point will move to this, but I'm not going to calculate this. I only focus on x1 direction, so only this tiny length is our focus in x1, right? So where is it? This angle, and you know this one is epsilon y dy, and we know that this is theta. Okay, so sine, this is epsilon y dy sine theta. So because of epsilon y dy move toward y direction, it makes this point become here, and it become here in x1 direction. It moved epsilon y dy sine theta. Okay, so this is the second contribution. Yeah, that's fine. Okay, and this one, this rectangle has the shear stress, the shear strength, gamma xy, gamma xy, and it makes this point move to here, okay, and move to here, and this shear contribution will make this point to here, and the x1 direction, it increase gamma xy dy cosine theta. So actually, is this okay? This this triangle. And how can we get that? Okay, so this is gamma xy, right? So your gamma xy times dy will be this length, because this is a kind of pizza shape, right? Pizza shape. So you can get this gamma xy dy times cosine theta. You can get this increment due to the gamma xy. So this is the third contribution. So delta D has three contributions: epsilon x, epsilon y, gamma xy, and then this is total elongation. We divide by ds. What is ds? The original length. So it will be epsilon x1, right? So dx divided by ds, dy divided by ds, dy divided by ds. What are they? They are what are they? Dx over ds. Dx over ds. Hey, theta. Cosine theta. Okay? Dy over ds. Dy here. Dy and ds. Oh, theta is sine theta. Okay? Beautiful. All right, so we can change dx over ds become cosine theta. Dy over ds becomes sine theta. And then epsilon xy has this transformation equation. And then we can get that. All right. Well, the reason why I'm gonna say this is a little bit difficult because this is kind of out of the scope of 95% of the proof in mechanics of material, right? This is pure geometry things. 应该听懂我在讲什么吧？哈，我觉得我这边讲的就算是很清楚的哦。总之就是 S 方向、X1 方向的生产量有3个贡献。你动了 epsilon x， 你就会连带的动到那个点，在 x1 方向上。你把 x1 epsilon x 的 epsilon y 跟 gamma xy 动到那个点，在 x1 方向上的共性全部加总起来，就得到了，就得到答案。而且运气很好的是 dx 除以 ds，dy 除以 ds 刚好也是 cosine theta 跟 sin theta， 所以就把那个 dx 跟 ds。dx 跟 ds 消掉 ，OK， 你这是运气不错。接下来呢更难了哈，但是我觉得这是 concept 是一样的了，一样的绘图。Next one is a little bit complicated, but I would like to say the concept is the same. Concept is the same. All right. Now, let's determine gamma x1, y1. This is a little bit more difficult. Let's take a look. Okay, so remember that gamma x1, y1 is a shear strength, right? So you can imagine that we also have 3 contributions due to epsilon x, epsilon y, gamma xy. Again, the same. We want to see these 3 contributions in gamma x1, y1. So what is gamma x1, y1? Of course, it's the angle rotation of x1. Okay, so you can see that due to the epsilon x dx, what will this point rotate to this point? The rotation, the angle here is now our focus here. Okay, and you see, so, and also this is a little bit, you need to be careful. This is x, this is y, and this is x1, this is y1, right? Assume that we do the gamma x1, y1 is a kind of positive, right? So your shape will become like this. Okay? Okay, so your x1 will become this line. Your y1 will become this line. Okay, so x1 become the A line, y1 become the B line. Okay, so the total gamma x1, y1 will be alpha plus beta. Okay, but this is a little bit difficult, so I focus on alpha first. I want to see the x1 and rotate due to the 3 contribution. Okay, so this x1 rotate, and later we will determine beta. Okay, later, and alpha plus beta will be gamma x1 y1。听懂吗？就是 gamma x1 y1 就是 x 跟 y 轴不是这样嘛，原本然后后来变这样的角度的改变。那它有两个两个分类哈，就是一个是 x1 变，一个是 y1 变。OK， 那 x1 变的那个部分我们叫它 alpha，y1 变那边我叫它 beta。好，然后 alpha 呢的3个贡献。epsilon x 的贡献 ，epsilon y 的贡献，跟 gamma x y 的贡献。当然，贝塔角也会有这3个贡献。等一下我们再说，我们先 focus 在 alpha 好吗 ？So let's focus on alpha now. So x1 direction, you see x1 going counterclockwise. Okay, so you see alpha is counterclockwise. Okay, this is counterclockwise. You see here is counterclockwise. Okay, so actually, wow. I want you to emphasize here. I want you to notice here. Alpha is counterclockwise, but you see, if you have positive epsilon x dx, it will make this point to here. It will generating clockwise direction of the angle change. So this one will make it minus sign. And again, this one, x, due to the y extension, you will have counterclockwise. So, okay, this is positive. But if you do the gamma xy, you will also make it downward, I mean the clockwise. So it's also minus sign. Okay, so minus, positive, minus. Because of the rotation direction, you need to be careful. Apart from this, everything is similar to the previous page. Okay, again, we have this angle, triangle. Okay, and this is theta. Okay, so again, epsilon x dx times, this should be it should be this one. Okay. This length, the length here, I should here. This triangle height, this one. Okay, we need this one and divide by the ds, and we can get the angle of this. Okay, so here, I will say this. Sorry. This is epsilon x dx sine theta. Okay, but this one is is okay, epsilon x dx sine theta. And how to get the angle? We divide by ds. So because this is the pie shape, right? This is a pizza shape, 扇形。你用弧长除以它的半径，你就可以得到它的角度的开角的变化。So 这就是一个开角的变化。Okay, so this is the open angle of this due to the epsilon x. Again, if you have a second epsilon y dy, so you move this point to here and make this red line rotate along this angle. Okay, so this width will be epsilon y dy cosine theta. Okay, and this is here epsilon y dy cosine theta. Again, divide by ds, you can get this angle. Okay, finally, very similar to what we learned before. Okay, if we has the gamma xy, you will make this point to here, and you will make this line rotate about this angle. Okay, and this angle needs to get this length. This length is gamma xy dy sine theta. Okay, so this is gamma xy dy sine theta divided by ds, and then you will get the angle here. Okay, we will do exactly the same thing. Blah 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 blah, and you get the alpha equal to this. Oh, by the way, the alpha has 3 contributions, right? Epsilon x we call alpha 1. Epsilon y alpha 2, gamma xy alpha 3. Okay, so summing up together, your alpha become very ugly term here. Don't worry. Okay, now you see, wow, this is so complicated. We have alpha, and then we are going to determine beta. Wow, too difficult. But it's okay. We have a trick. Okay, we have a trick. Don't worry about this. We have a trick. Okay, what trick? Here, you see, alpha here is counterclockwise. Beta here is clockwise. Okay, this is clockwise. So you will notice that they has different sign clockwise. They will have different sign. So what I will do here is substitute theta plus 90 degree and add minus sign. Oh, what does that mean? You see, x1 direction is here, but actually y1 is the theta plus 90, become a new x1. So your y1 actually is a new x1 with the theta equal to theta plus 90 degree. Okay, so but what you learn here is positive. I mean counterclockwise. But now your beta is clockwise. Sorry, it's opposite side. So you need to add minus sign. Okay, because beta is clockwise, which is opposite side to counterclockwise alpha. So all you need to do is adding theta, become theta plus 90, and then get the minus sign. So your beta equal to blah, 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 blah. Okay, you don't need to determine whole things altogether. Again, no, you don't need to do that. All you need to do is substitute theta plus 90 degree and adding minus sign. Okay, so you can get this, and you sum it up together, alpha plus beta become blah, 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 blah. Ugly, I know, it's okay. So that's it. I guess the concept's easy, okay, but you need to understand the three contribution. Okay, three contribution is very important. And also the alpha and beta relationship. That's the key here. Then we will do the plane strain transformation equation. It will look very similar to previously plane stress. Very similar. Very similar. Okay. We also need to use the sine, cosine, and double angle, half angle things. Okay. Now, combine all these together. All right. I can get the next page. Plane strain, or it's not conversion. It should be transformation. I'm sorry. Transformation. Okay. Sorry, this is not conversion. And I will say epsilon x1, gamma x1, y1 is very important. Okay. If we use this sine 2 theta, cosine 2 theta things, we can make it looks relatively similar to what we learned in plane stress. You see, average strain minus then divided by 2 cosine 2 theta. Okay, so very similar to what we learned. Okay, yeah, that's it. And also we have strain invariant, just like sigma x1, sigma y1. You see, epsilon x plus epsilon y equal to epsilon x1 plus epsilon y1. Okay, so very similar. And you can expect exactly the same thing in plane strain. Okay, because you have the cosine, sine, you have principal strain. Okay, principal strain, very similar. So it will be really quick because you learned that before, right? So plane strain, very similar. Okay, we do the differentiation, then make set it equal to 0, and we can have tangent 2 theta p, and then you can give exactly the same thing. Your plane strain equal to average plus and minus r. Okay, so very, very similar to what we learned. Almost the same. Okay, and maximum shear strength, almost the same as well. Do exactly the same thing, and gamma max divided by 2, epsilon 1 minus epsilon 2 divided by 2. Okay, very, very similar. And then you can expect that you will have plane strain Mohr circle because everything is the same. Everything is the same. Okay, and again, epsilon x1 and gamma x1, y1 divided by 2 will be positive to the right, positive to the bottom, to the down wall, And I want you to emphasize here is that your sigma x1, of course, replaced with epsilon x1 in the plane strain case. But y1 you need to divide by 2. Okay, 2. So you need to be careful, a little bit careful here. Okay? Yeah. 就这边跟前面都一模一样啊，所以我们这边就可以跳过。但是这边要注意一件事情，就是你的 tau xy 跟你的 gamma x1 y1 divide by 2，哦，这边会比较，这边要小心，要除以2。为什么？因为你作为一个 tau x1 y1，你就会有对 x1 轴跟 y1 轴都有各自的 gamma，所以你如果只针对一个方向的话，你只看得到一半，好，所以这边要小心。So the reason why tau x1 y1 need to be replaced by gamma x1 y1 divided by 2 is because that because we only focus on one direction, right? So if you have gamma x1 y1, you will have two contribution, half of it. Okay, so that's why we only have gamma x1 y1 so divided by 2. Okay, in the Mohr circle. All right. 我觉得我好像教不完呢，尤其是最后一题。Anyway, right. So let's finish this part. And tomorrow, well, actually, I recorded this. Problem in the video. Okay, so I only left one video for this. Actually, I recorded this already. Okay, and I can upload this as well. 好，讲中文就是我发现教不完啊，因为有2题。好，那我觉得我等一下的时间只剩1题的时间。那这一题教完以后，最后一个题目呢，我会用上传影片的方式。那这影片其实我早就录好了，因为这件事情发生过了哈，就是我也有以前发生过这件事情，11年来发生过一次，所以这我早就录好了，我才把那个影片传上去给大家看。那对，就这样。Okay, so let's continue to final example. All right. So consider the plane strain should like this. So you can imagine that you have a whatever shape material, okay, and you have a whatever loading. I don't care. I don't know. And you have a strain element in some part of the material, and then you see this strain element after the loading become this shape. Okay, and this has the 340 times 10 to minus 6, and y direction has 110 times 10 to minus 6, and 180 times 10 to minus 6 in shear. Okay, so what is the strain of the element if you have a material, what will it looks like if the same point has the 30-degree? Okay, and what will it look like after deformation? I mean, what will it look like? 听得懂吗？就是有一个材料长随便什么形状，它在受力之前，你画一个方块在上面，然后你受力之后，随便怎么受力，管它的，反正受力完以后，哎，这个形状变成这样子的，然后这形状可以量测出来 x 方向、y 方向跟剪切的应变是多少，我可以量测出来哦。 那如果今天我在同样的位置画了一个30度倾角的东西的 strain element 长这样子，那同样的力量，同一个点，它这个形状会长什么样子？那他就是要问我这个问题。Okay, so theta a theta equal to 30 degrees. All right, I need to, before we do that, it's good to have the average prepared. All right, so it's 340 plus 110 times 10 to minus 6 divided by 2. 225 times 10 to minus 6. And the other is epsilon x minus epsilon y divided by 2 equal to 340 minus 110 divided by 2 times 10 to minus 6. 115 times 10 to minus 6. Gamma xy divided by 2. 90 times 10 to minus 6. Okay, so theta equal to 30. Epsilon x1 equal to 225 plus 115 cosine 60 degree plus 90 sine 60 degree times 10 to minus 6. Okay, equal to 36, 360 times 10 to minus 6. Epsilon y1 invariant. Okay, epsilon x plus epsilon y minus epsilon x1 equal to 90 times 10 to minus 6 tau x, sorry, gamma xy, gamma x1 y1 divided by 2 minus 115 times sine 60 plus 90 cosine 60 degree times 10 to minus 6. So gamma x1 y1 equal to minus 110 times 10 to minus 6. Okay, so you have 30-degree value. So it's easy for us to get the strain element. Okay, this is 30-degree. Previously, it looks like a perfect. Previously, it looks like a perfect shape, right? Just like this. All right. Now, after the whatever yellow loading, it becomes okay. X1 direction 360 times 10 to minus 6 positive. So it increased from this point to here. And this direction is 360 times 10 to minus 6. Okay. Y direction 90. From this point to here. So it's 90 times 10 to minus 6. Okay. Then gamma is minus 110 times 10 to minus 6. So you see, positive stress, shear stress will make it to the right hand side. The negative will to the left hand side. So this is 1, 1, 0 times 10 to minus 6. So now you are ready. See? This is the direction. This is the shear direction. Connecting them. All right, so this is the strain element. So it will look like this. Okay? Don't forget, these 4 elements are all in the same point. 这4个方块都其实是在同一个点上哦。不要因为我画的有点歪歪的，它其实在同一个点上，它在同一个点上，同一个应变的状态，只是不同的方位而已。就你一开始画那个方块长相，变形以后就会长这个样子。还蛮有趣的，它可以预测你在一个材料上画一个图案，它变成什么样子，蛮有趣的。OK， and it asks us， 哇，我真的上不完，真是的，太有自信。OK， 我看来我要重录因为连第 C 小题我都上不完，哈哈哈。真麻烦。Okay, I guess I can only finish the principal strain part. Okay, maybe even cannot finish that yet. 3 minutes. Anyway， 不上3分钟，太多了，太少了，也上不完。好，那我全部都用录的，就接下来都用录 upload 给你，好不好？那就这样。那还有 C 就是 gamma mix。好，那所以我觉得还是大家想明天来上课，我是没意见了。大家想明天来上课吗？我是没差哦，这样我不用录，我反而更开心。不然的话，投个票好了，在场的同学对吧？剩2分钟投票。大家希望我明天再上课，还是我直接把它录成影片上传？举手。赞成明天上课请举手。赞成录影的请举手。都没有啊，我同意，要表示一下意见。表示一下意见，大家觉得怎么样？录影都可以，录影都可以，所以就是录影。好，那我就录影，明天就不用上课。OK， 好，谢谢大家。有问题可以来问哦，因为我这次上得快，所以我相信可能会大家有点问题，来问吧。有小考的问题也可以问他。嘿，是的，明天不用上课。哎，但我要回家录。